So now whether screen is visible to everybody?
Yes, sir.
Yes, yes, visible.
Okay. So we'll take the short review related to the surface tension. So we are knowing the definition of surface tension. Wait. Okay. We are knowing the definition of surface tension. So whatever surface tension is nothing, surface tension is there. That surface tension is nothing but the tensile force acting on the surface of liquid, which is in contact with two immiscible fluids. That means in contact with gas and liquid, such that their contact surface behave like membrane under tension. So the surface tension, whatever surface tension phenomenon is there, that is mainly occurred because of the cohesive forces between fluids at the surface of the fluid. And the SI unit of surface tension is Newton per meter. After that, we have seen the derivation related to the surface tension on a liquid droplet. So here we have considered one liquid droplet. So whatever liquid droplet will be there, that will be in spherical shape. So if I am going to consider d is nothing but the diameter of that liquid droplet, p is nothing but the pressure intensity acting inside the liquid droplet, and sigma is nothing but the surface tension acting on a liquid droplet. And if I am going to cut this liquid droplet which is spherical in shape by half portion, then haircut section of that liquid droplet will be look likewise. So here whatever outer periphery is there, so on that liquid droplet, so whatever outer periphery will be there, there will be the interface between liquid and air. So whatever surface tension or whatever tensile force will be acting, that tensile force acting on that droplet. So as we are knowing that I will take a half portion of this droplet. So if I consider the free body diagram for that liquid droplet, then two types of forces will be acting on that liquid droplet. First one will be the tensile force, second one will be the pressure force. So out of that, whatever tensile force will be there, that tensile force will be acting on the periphery of that liquid droplet. So here in this diagram, you will observe that sigma is nothing but the tensile force which is acting on the periphery of that liquid droplet. So here value of tensile force due to surface tension acting around the circumference of the cut portion, that will be equal to sigma into circumference. So if I am considering d is the diameter of that liquid droplet, then circumference will be equal to pi d. So tensile force acting on that liquid droplet will be equal to sigma into pi d. So this is the first force which is acting on that liquid droplet. Then second force will be acting because of the pressure intensity. So here on the same half portion of that liquid droplet, whatever inner portion will be there, that will be filled with the liquid. So on that inner portion, that pressure intensity will be acting in the opposite direction. So here if I am considering P is nothing but the pressure intensity, then total pressure force acting on the entire liquid droplet will be equal to P into area. So whatever inner area will be there, that inner area is nothing but pi by 4 d square. So pressure force acting on that liquid droplet will be equal to P into pi by 4 d square. So here for equilibrium, the surface tension force and tensile force and pressure force will be same. That's why if I'm going to equate both the equation, that is nothing but equation 1 and equation 2, tensile force and pressure force acting on the same liquid droplet, then P into pi by 4 d square is equal to sigma into pi d. Here pi will get cancelled, dd will get cancelled, and here I will get that value of pressure intensity P. So value of pressure intensity P will be equal to 4 sigma upon d. So this is the value of pressure force acting on a liquid droplet, whereas sigma is called as a tensile force, d is called as a diameter of that liquid droplet. So this is the tensile force acting on the, or this is nothing but the pressure force acting on the liquid droplet. Then we have seen the surface tension acting on a hollow bubble. So for hollow bubble means same liquid droplet, only whatever that liquid droplet will be there, the inner portion of that liquid droplet will be containing the air, that is nothing but the halo. So here if I'm going to consider the same liquid droplet, but that instead of liquid droplet I'm going to consider that as a halo bubble. So here if I'm considering d is nothing but the diameter of that halo bubble, and sigma is nothing but the pressure intensity acting inside the halo bubble, and sigma is nothing but the surface tension acting on that halo bubble. So if I'm going to consider the cross section of that halo bubble, now here we are knowing that two
Correct, sir.
forces are acting. First one, yes,
Many students are waiting to join, so that messages are coming on the group. So, if possible, you just join all the students.
what is happening as I'm sharing my mobile screen. So
Okay.
I have to exit this presentation and after that I have to join. Okay, I will take a 2 minute and within 2 minutes I will join.
Take 2 minutes and join all. Then once again, start the lecture.
Oh, how to exit the screen? Correct, sir. Hello.
Hello.
How to exit that presentation?
Stop sharing. That option is there, no? Stop screen sharing at the top.
Can you drop one message, Parke sir? Within
Ah,
1 minute, if anybody want to join, you can join. Afterwards, it will not be possible to join them for
okay.
the lecture.
Yes. Yes.
Shall I start? Or shall I wait for 1 minute? And
1 minute.
okay. You can also drop the message, remaining student, if your friend is waiting. If he want to join the lecture, he should join now only, because it will not be possible for me to admit him afterwards.
Yes, sir. Yes, okay.
Total count is 67.
हाँ सर, स्टार्ट कर.
Okay, okay. Now whether screen is visible?
No sir.
Not it. Now?
Yes sir, now it is visible.
Okay. So so second one is the surface tension on the halo bubble. So we have considered the same liquid droplet which is only halo in shape or which is halo. So here if I'm going to consider the surface tension, or if I'm going to consider the tensile force acting on that halo bubble. So as that liquid droplet is having two interface of liquid and air, that means at the outer periphery there will be the liquid air interface, and as that bubble is hollow, that's why at the inner of that bubble also there will be the liquid and air interface. So we are knowing that whatever surface tension or whatever tensile force is acting, that tensile force is acting at the interface between two immiscible liquid, that means at the interface between liquid and air. So here whatever tensile force will be acting, so that tensile force will be the two times that of tensile force which was acting in the liquid droplet, because at the outer periphery also and at the inner periphery also, as there is a liquid air interface, that's why tensile force acting on this hollow bubble will be equal to 2 sigma into pi d, that is nothing but circumference. So 2 into sigma into pi d. Pi we have considered 2 because at the inner surface as well as at the outer surface, as liquid air interface is there, that's why tensile force will be double. And second one is the pressure force which is acting in the opposite direction. So here on the same hollow bubble, whatever pressure force will be acting, that pressure force will be acting on that inside that hollow bubble. And if I want to calculate the value of pressure force acting on that hollow bubble, then that will be equal to pressure intensity P into area of that hollow bubble. So area of hollow bubble is nothing but pi by 4 d square. So P into pi by 4 d square, so that is nothing but the pressure force. Now here for equilibrium condition, tensile force and pressure force acting on that hollow bubble will be equal to same. That's why here next equation will be equal to P into pi by 4 d square is equal to 2 into sigma into pi d. So here if I'm going to cancel the term, that is nothing but pi and d term, then here I will get that value of pressure intensity acting on the hollow bubble is nothing but 8 sigma upon d. So now next equation or next derivation is nothing but the surface tension acting on a liquid jet. So suppose you are having one nozzle, and through that nozzle, suppose liquid is coming out in the form of jet of liquid. So here consider you are having a jet of liquid which is having the diameter as a d, and length of that jet of liquid is nothing but L. Now here if I'm going to take the cut section of this jet of liquid, then cut section of this jet of liquid, here I have considered the jet which is having diameter d, length L. So on this jet of liquid, P is nothing but pressure intensity which will be acting on the jet of liquid. Sigma is nothing but surface tension acting on the jet of liquid. Now if I'm going to take the cross section or cut section of this jet of liquid, then here you will observe that at the interference between or at the interface between liquid and air, there will be the action of the surface tension or tensile force. So here sigma is nothing but the tensile force which is acting on that jet of liquid, and that jet of liquid is having the length as a L, diameter is nothing but D. Now in this case, from both the side, that means from the left side as well as from the right side, that tensile force is acting over entire length equal to L. So here if I want to calculate tensile force acting, if I want to calculate tensile force acting on the jet of liquid, that will be equal to sigma into twice L, because that tensile force is acting on the left side as well as right side, which is having the length equal to L. So twice L into sigma is nothing but the tensile force acting on the jet of liquid. Here pressure force is also acting on that jet of liquid. So here if I am going to consider the pressure force acting on that jet of liquid, wait, so that pressure force will be equal to, so whatever inner surface is there, on that inner surface that pressure force will be acting. So pressure force will be equal to pressure intensity P into area of semi jet. So here whatever area will be there, so whatever that cross sectional area is there, so we have to consider that cross sectional area, and that cross sectional area, that is nothing but area of semi jet, will be equal to length L and diameter D. So pressure force acting on the jet of liquid will be equal to P into L into D. Now for equilibrium condition, we are knowing that tensile force acting on that jet of liquid and pressure force acting on that jet of liquid are same. That's why here if I am going to equate both the equation, so after equating both the equation, I will get that PL into D, that is nothing but pressure force, is equal to sigma into twice L, that is nothing but the surface tension or tensile force. So here L will get cancelled, and I will get that P is equal to twice sigma upon D. P is equal to twice sigma upon D, that is nothing but the tensile force acting on a liquid jet. Are you getting? So related to the surface tension, you have to remember some points which are very much important for solving the problem, as well as multiple choice questions are considered. So first point you have to consider. First point you have to remember, that is nothing but whatever tensile or whatever surface tension phenomenon is there. That surface tension phenomenon is mainly occur because of the cohesive force of attraction between the fluid molecules. Then second important point you have to keep in mind that the SI unit of surface tension is nothing but Newton per meter. Then related to the pressure inside the curved surface. So first point, if you want to consider or if you want to calculate the pressure force acting on a in general curved surface, which is having the radius of curvature as a R1 and R2, then the value of pressure force or value of pressure or delta P acting on that in general curved surface will be equal to delta P is equal to sigma into 1 upon R1 plus 1 upon R2. So if they are not going to mention that as a liquid droplet, that as a halo bubble, or that as a jet of liquid, and if they are going to consider any surface or any shape, and if they are going to provide you the two values, that means inner radius and outer radius or radius of curvature, then you have to use this equation. Then second one, pressure inside the water droplet, we are knowing the value of pressure inside the water droplet, that is nothing but 4 sigma upon D. Then third one, pressure inside the soap bubble, value of pressure inside the soap bubble is nothing but 8 sigma upon D. And last one, pressure on a liquid jet. So pressure on a liquid jet is nothing but twice sigma upon D. You have to remember these points related to the surface tension. Are you getting? Yes or no? Now we will solve the problems based on the surface tension. So first question. Surface tension is due to, four options are there. This question was asked for IS 1998. So chat box is open for you. You can drop your answers. Why the strength is decreasing? 58 students. Prajwal,
Yes, sir.
take the screenshot of attendance now only and share
Okay,
me
sir.
that screen. Okay.
Yes, sir.
Okay. Most of the students are writing the answer as a B. So we are knowing that whatever surface tension phenomenon is there, that is mainly caused because of the cohesive force of attraction. So answer is the correct answer. So surface tension is caused because of the cohesive force of attraction. Then next question. What is the pressure difference between inside and outside of a droplet of a water? What is the pressure difference between inside and outside of a water droplet? Twice sigma upon D, 4 sigma upon D, 8 sigma upon D, 12 sigma upon D, where sigma is the surface tension and D is the diameter of droplet. IS 2008. Give the answer. Remaining student. Any another? So pressure difference between inside and outside of the droplet of water. That means delta P for droplet of water or water droplet. We are knowing the formula. What is the delta P for water droplet? 4 sigma upon D uh, for soap bubble or for bubble, sigma, and for liquid jet twice sigma upon D. Then next question. So option B is the correct one. Next question. If the surface tension of water-air interface is 0.073 Newton meter, the gauge pressure inside a raindrop of 1 mm diameter will be. So you have to solve the problem without using calci. If the surface tension of water-air interface is 0.073 Newton meter, that means they have provided the value of Newton meter, that is nothing but sigma. The gauge pressure inside a raindrop of 1 mm diameter, that they have provided the value of D also. So as they have mentioned that a raindrop, so a raindrop is nothing but the example of liquid droplet, not the hello bubble. So you have to use the formula for liquid droplet. Important thing is you have to you have to do the unit conversion. Unit conversion is important factor. Calculate the answer. Don't copy from the others, because once any student writing the answer as a B, everybody is writing B. If anybody is writing D, everybody is writing D. Don't follow that method. You have to calculate, and if your answer is that same answer, put the same answer, no issue. So most of the students are writing the answer as a D, and correct answer is option D, because we are knowing that for liquid droplet formula is P is equal to, or delta P is equal to 4 sigma upon D. So 4 into sigma. What is the value of sigma? 0.073. And value of D, as they are mentioned in terms of mm. So whatever sigma value is there, that value of sigma is in terms of Newton per meter. So you have to convert that mm in terms of meter. That is nothing but 1 mm is nothing but 0.001. So your answer will be 292 Newton per meter square. Then next question, what is the pressure inside a soap bubble over a atmospheric pressure if its diameter is 2 centimeter and surface tension is 0.1 Newton meter? Similar to the previous problem. This problem also, this also you have to solve. Only thing they have mentioned that pressure inside a soap bubble. So for soap bubble, formula is 8 sigma upon D. Remaining student, I am seeing the chat box. Only same students are writing the answer. Near about 62 students are present. So option C is the correct one, because here which formula you have to use? Delta P is equal to 8 sigma upon D, because here they have mentioned the soap bubble, and 8 into sigma, value of sigma is 0.1 Newton per meter, and upon D here 2 centimeter they have mentioned. You have to convert that centimeter in terms of meter only. So you will get the option C. Now next concept called as a capillarity. So we are knowing the definition of capillarity. So in general definition of capillarity means it is the phenomenon in which rise or fall of liquid surface in a small tube related to the adjacent general level of a liquid when that tube is held vertically in a liquid. That means, in simple word, capillarity is nothing but the process, or capillarity is nothing but the rise or fall of liquid level above its general level or below its general level. So whatever capillarity action is there, that capillarity action is mainly caused because of the cohesive as well as adhesive force of attraction. So what is meant by cohesive force of attraction? Cohesive force of attraction is nothing but force of attraction between two similar molecules. And adhesive force of attraction means force of attraction between two dissimilar molecules, that will be called as the adhesive force of attraction. Whatever this capillarity phenomenon is there, you have to keep in mind that surface tension phenomenon is occurring mainly because of the cohesive force of attraction, whereas capillarity phenomenon is occurring mainly because of the cohesive as well as adhesive force of attraction. Now the whatever rise of liquid level will be there inside the capillary tube, that will be called as a capillary rise. Whatever fall of liquid level will be there inside the capillary tube, that will be called as a fall of capillary tube, or that will be also called as a capillary depression. And important thing, whatever capillarity term is there, that will be expressed, that means unit of capillarity will be either centimeter of liquid column or of liquid column. And as I have mentioned that capillary action is occurring mainly because of cohesive as well as adhesive force of attraction. So whatever capillary action is there, or whatever value of capillarity is there, that is mainly depend upon surface tension, material of the tube, then specific weight of the liquid, and diameter of the tube, as well as surface tension of the liquid also. So those are the various parameters which are affecting on the capillary action. Now there are two terms. First one is called as a capillary rise. Second one is called as a capillary depression. Capillary rise means rise of water level inside a capillary tube. Capillary tube means a tube which is a glass tube which is having very small diameter. So capillary rise means the tube in which the level of liquid will goes on rising above the surrounding level or above its surrounding level of the same liquid, that will be called as a capillary rise. So as we are knowing that if I'm going to consider the example as a water, so inside the water, if I'm going to insert a capillary tube, that means a very small diameter tube which is having the diameter D, and both end of that tubes are open. If I'm going to place that tube vertically, then I will observe that the level of water inside the capillary tube is higher than the general level of that water surrounding to that capillary tube. So whatever that rise of liquid or whatever that rise of water inside the capillary tube will be there, that will be called as a capillary rise. Here in this picture, you are clearly observing that there is one container, and in that container I have the water as a liquid, and in that water I'm going to insert a capillary tube which is having the diameter D. So when I'm going to insert that capillary tube which is having the diameter D, then I will observe that there is a rise of water inside the capillary tube. And here H is indicating height of the liquid level inside the capillary tube above the general level of the surrounding liquid. And here you will observe that sigma is nothing but tensile force, and the angle made by sigma with the capillary tube is nothing but the theta. So why there is a capillary rise, or why there is a, or when there will be the capillary rise and when there will be the capillary fall. So here, if you are going to observe this picture carefully, so if the value of adhesive force of attraction, if the value of adhesive force of attraction between that liquid molecule and glass tube is more than value of cohesive force of attraction between the same liquid molecule, then there will be the rise of liquid level inside a capillary tube. That means in case of water, whatever adhesive force of attraction between water and glass molecule, why I am considering the glass molecule, because whatever capillary tube is there, that capillary tube is made up of glass molecule. So here, if the value of adhesive force of attraction between water and glass molecule is higher than the cohesive force of attraction between two water molecules, then and then only there will be the rise of water inside a capillary tube. So here, in case of water, there will be the rise of capillary tube. So here, I have to find out the expression for capillarity rise. That means I have to find out the value of H. So for that purpose, I have considered this tube or this capillary tube which is inserted inside a water. So here, because of this rise of liquid, so if I'm going to consider the equilibrium condition, so that means if I'm going to draw the free body diagram, so here two forces will be acting. So first force will be tensile force which is acting. First force will be tensile force which is acting on the surface of water, and that tensile force acting in the vertically upward direction. And second force is nothing but the weight of water inside a capillary tube above its general level. So under state of equilibrium, the weight of liquid of height h is balanced by the force at the surface of a liquid in the tube. So whatever force at the surface of liquid in the tube is there, that is called as a surface tension. So first of all, if I'm going to calculate the weight of water, or weight of liquid of height h, then here weight of water which is inside a capillary tube of height h will be equal to volume of that capillary tube which is having the height as a h into rho into g, because I'm knowing that weight density is nothing but rho upon volume. Weight density means what is the weight density? Weight density means rho g upon volume. So weight is nothing but volume into rho g. So here volume is nothing but area of tube into h into rho g, that is nothing but the weight of liquid having height h in the tube. And second one is nothing but the tensile force. So here area of tube is nothing but pi by 4 d square, because d is nothing but the diameter of that capillary tube. So pi by 4 d square into h into rho into g. This is nothing but the formula of weight of liquid inside a capillary tube which is having the height h. So here of that liquid is nothing but is balanced by the surface tension, or that is balanced by the tensile force. So tensile force is nothing but sigma. So here this weight is acting in the vertically downward direction. So whatever sigma will be there, that sigma will be acting in the vertically upward direction. So here if I want to calculate the vertical component of the tensile force, so here at the top of that capillary tube, you are observing that sigma is nothing but the tensile force which is acting on the surface in the capillary tube, and that sigma is making an angle theta. So if I want to consider the vertical angle or vertically upward component of that sigma, then here vertically upward component of that sigma is nothing but, so here that entire sigma is acting over the circumference, that is nothing but pi into small d, whereas small d is nothing but the diameter of tube. So sigma into pi d into cos theta, that is nothing but the vertical component of the tensile force. So here sigma into pi d into cos theta, that is nothing but the vertical component of the tensile force. Now here both the forces are under equilibrium, both the forces are balancing each other. That means weight of liquid inside a capillary tube having height h is balanced by the vertical component of tensile force. So here if I am going to consider, or if I am going to equate both the equation, then after equating both the equation I will get that. So for equilibrium condition I am going to equate both the equation, that is nothing but weight is equal to tensile force. So weight is nothing but pi by 4 d square into h into rho g is equal to tensile force, or vertical component of tensile force is nothing but sigma into pi d into cos theta. So my ultimate aim is to find out the value of h, that is nothing but capillary rise. So value of h will be, that means by rearranging the term, value of h will be, so another term, another side sigma into pi d into cos theta divided by whatever term which is along with h, that will come under the in the denominator. So pi by 4 d square into rho g. So pi pi will get cancelled, dd will get cancelled, and I will get the equation as a h is equal to 4 sigma cos theta upon rho g into d. I'm getting the equation as a 4 sigma cos theta into rho g into d. This is the general equation. This is the general equation for capillary rise or capillary fall. But here, if I'm going to consider the example of water. So in case of water, there is a capillary rise. So for water and for glass tube, for water and for glass tube, the value of theta is equal to 0 degree. Value of theta is equal to 0 degree. So if I'm going to put the value of theta as a 0 degree in this equation of h, then cos 0 is nothing but equal to 1. So I will get the value of capillary rise. So you have to remember this formula. So value of capillary rise inside a capillary tube will be given by equation 4 sigma upon rho into g into d, whereas h is called as a capillary rise, sigma is called as a tensile force or surface tension. Sigma is nothing but surface tension, unit will be Newton per meter, rho density of the fluid, g gravitational acceleration, and small d is called as a diameter of a capillary tube. So if you are knowing the value of sigma, rho, g, and diameter of capillary tube, you are able to calculate the rise of water level inside a capillary tube. That is called as a capillary rise. Are you getting? Similarly, we have to find out the expression for capillary fall. So as I have mentioned that capillary rise is occurring when adhesive force of attraction is having higher value as compared to the cohesive force of attraction. That means in case of water and glass molecule, that means adhesive force is having higher value as compared to any two water molecule. That's why there was a rise of water level inside the capillary tube. But if you are going to take the example of a mercury, and if in one container, if you are going to take the mercury, and inside the mercury, if you are going to dip the capillary tube vertically, or if you are going to insert that capillary tube vertically, then you will observe that mercury level will goes on decreasing as compared to the surrounding level of that mercury, because of insert or because of immersing that capillary tube. So why there is a fall of mercury inside a capillary tube? Because if you are going to consider the force of attraction between two mercury molecule, any two mercury molecule, that means cohesive force of attraction between two mercury molecule is having higher value as compared to the adhesive force of attraction between mercury and glass molecule, as compared to the adhesive force of attraction between mercury and glass molecule. Hence there will be the fall of mercury level. So when there will be the fall of mercury level, if cohesive force of attraction between that fluid molecule is having higher value as compared to the adhesive force of attraction between that fluid molecule and glass molecule, then and then only there will be the fall of mercury level. Are you getting? So here also we have to find out the expression for capillary fall. So here in this diagram you are observing that there is one container. In that container there is a mercury, and inside that mercury, a capillary tube which is having the diameter as a small d is immersed vertically. So when that inside a mercury, the liquidity inside a capillary tube will goes on decreasing. H is nothing but the fall of mercury level. Here you are observing that H is nothing but fall of mercury level inside a capillary tube. Then whatever sigma is there, sigma is nothing but the tensile force acting on a mercury, and theta is nothing but angle made by uh, sigma, that is nothing but tensile force or surface tension with the vertical of mercury of glass tube. So here H is nothing but height of depression in a mercury. So for equilibrium condition, here also there will be two forces which will be acting on a mercury inside a tube. Here also in the fall of mercury or depression of capillarity also, there will be the two type of forces which will be acting on a mercury inside the capillary tube. So first force is nothing but the surface tension force. First tensile force, also called as a surface tension force. And second force, here if you are going to consider the surface tension force, so that surface tension force is acting in the vertically downward direction. Here sigma is nothing but the surface tension. Sigma is nothing but the tensile force. So surface acting over the circumference of into d. So here first one is nothing but surface tension acting in the vertically downward direction, that will be equal to sigma into pi d into cos theta. Pi cos theta, because that surface tension is making an angle theta. Surface tension is making an angle theta with the glass tube. And here as I have to consider the vertically downward component of that surface tension, so that will be equal to sigma into pi d into cos theta. And that sigma into pi d into cos theta, that is nothing but surface tension, will be balanced by intensity, or that is balanced by the hydrostatic force acting upon that mercury, which is at a depth equal to H. So here second force is due to hydrostatic force acting upward and is equal to intensity of pressure at depth H. So that intensity of pressure will be equal to P into pi by 4 d square. Here you are observing that at the downside there is a P, term P, and that pressure intensity at a height EH is acting in the vertically upward direction. So according to hydrostatic law, we are knowing that pressure intensity will be equal to P. That pressure intensity is acting over the area equal to pi by 4 d square. So here P into pi by 4 d square, where P is nothing but rho g h into pi by 4 d square. So these are the two forces which are acting in case of mercury or in case of depression of capillarity. So here under equilibrium condition, both the forces will be equal. So here if I'm going to equate both the forces, so first one is nothing but sigma into pi d into cos theta, that is nothing but the surface tension or tensile force which is acting in the vertically downward direction, and second force is nothing but because of the pressure intensity at a height eh, that is nothing but rho g h into pi by 4 d square. As our ultimate aim is to find out the capillarity fall, that is nothing but here also we have to find out the value of eh. So here value of eh will be rearrange the term. So after rearranging the term, here pi will get cancelled, d will get cancelled, and in general equation which we got in the previous case also, same equation here also I will get, that is nothing but h is equal to 4 sigma upon rho g d. In case of capillary rise, there was also same derivation, that is h is equal to 4 sigma cos theta upon rho g d, but their value of theta was equal to 0. That's why capillary rise was written by h is equal to 4 sigma upon rho g d. In case of capillarity fall, whatever general equation we are getting, that is the same, that is nothing but 4 sigma cos theta upon rho g d. Here whatever value of theta is there, in case of mercury and glass, you have to remember this both the value. That means value of theta for mercury and water is equal to 0, whereas value of theta for mercury, sorry, value of theta for water and glass is equal to 0, and second one value of theta for mercury and glass is equal to 138. So here if I'm going to put the value of theta as a 138 degree, then here that will be in the second quadrant. So here I am getting the value, that is final equation, as a h is equal to minus 4 sigma. Here minus term will be there because as we are getting the second quadrant. So cos of 180 minus 138, cos of 180 minus 138. So here I am getting that h is equal to minus 4 sigma cos of 42 degree divided by rho g d. So this is the equation. Here why negative sign is coming? Because there is a capillary depression. That means fall of liquid level inside the capillary tube. That's why I'm getting the negative sign. So h is equal to minus 4 sigma cos of 42 degree divided by rho g d. That will be the equation for calculation of capillarity fall. Are you getting? So for capillarity rise, equation is 4 sigma upon rho g d, whereas for capillarity fall, equation is h is equal to minus 4 sigma cos of 42 degree divided by rho g into d. And we have to keep in mind that whatever capillary fall or capillary rise is there, that is mainly because of adhesive as well as cohesive force of attraction. If adhesive force of attraction is having higher value as compared to cohesive force of attraction, then there will be the capillary rise. And if cohesive force of attraction is having higher value as compared to adhesive force of attraction, then there will be the capillary fall. So last note, if adhesion is more than cohesion, then wetting tendency is more and the angle of contact is smaller. So this is related to the capillarity. So now we have to solve the problems based on the capillarity. So the formulas which we are going to use, first formula will be for capillary rise, h is equal to 4 sigma upon rho g d. Second, for capillary fall, h is equal to minus 4 sigma cos of 42 degree divided by rho g d. angle theta for water and glass is equal to 0. Angle theta for mercury and glass is equal to 138 degree. Capillarity is caused mainly because of adhesive force of attraction and cohesive force of attraction. And last 2 point, capillary rise is occurring mainly because when adhesive force is having higher value as compared to cohesive force, capillary fall is occurring mainly because when cohesive force is having higher value as compared to adhesive force of attraction. So those are the key points or points to be remembered related to the capillarity. Now what is the time?
So it's 11.
Okay, it's 11. Whether Parke sir is there?
Sir, Parke sir has shared the link in the group.
Okay. Parke sir has shared the link in the group. So now whatever problems will be there based on the capillarity, we are going to take the problems based on capillarity in the next lecture. Prajwal, have you taken the screenshot of attendance?
Yes,